Log on, tune in, find out. Another good idea from Cambridge.
Scientific program, and the first speaker today is Katrin Becker.
Right. Well, thank you very much for the invitation to give this talk. So this talk is based on work done in collaboration with Guan Gu and Daniel Robbins. So we have written 3 papers on the topic, and there are still some dots here, so some papers that we have to write. So I will be discussing. Is this working? Probably. Okay. So I will be discussing the computation of superstring scattering amplitudes on worksheets with the topology of the disk or RP2 with closed or open string insertions. So we will be interested in type 2 string theory. So why do we want to do this, and why hasn't this done before? I mean, this is perturbative string theory. Well, one of the purposes is to extract information about the D-brane and orientifold plane effective action. So to do this, we will compute certain string scattering amplitudes, and then we will take the field theory limit. We will discover new terms in the D-brane and orientifold plane effective actions. So the novelty of some of the terms that we are going to find is, first of all, they are higher order derivatives, so they are fourth order derivatives, and moreover they include not only the metric but also the B field. We will see that some of these terms are actually needed to restore consistency of string theory. Now, so yesterday Ruben gave a nice collection or a long list of motivations why it is interesting or useful to include the B field in higher derivative terms. So this means I can skip that. And so the only motivation I'm going to give you is that we need them to restore consistency. Now, so this is a summary of basically what I just said. So I will start my talk just by setting up the tools that we need to compute these amplitudes. Well, most of these tools you would think are known because, again, this is perturbative string theory. But back in the 80s, when people were setting up technology for perturbative string theory, topologies like the disk were considered like exotic, so people really didn't bother. So we ended up actually setting up all the technology needed from scratch, and to our surprise, we were even able to obtain some new results. So I will spend some time showing how we set up this technology to compute the superstring scattering amplitudes, and I will show that these are reliable objects. So I will talk about some of their properties. Now, then I will come to some concrete examples. I will discuss concretely a 2-point function of one Ramon-Ramon field and one NS-NS field. And I will also mention a 3-point function of one Ramon-Ramon field and 2 NS-NS fields. So once we have these objects, we want to take the field theory limit, so a small momentum basically, and then we are going to extract the new interactions on the D-brane volume. And then I'm going to explain how these new interactions are needed to restore consistency of the D-brane effective action. So let's start with setting up the tools. Well, we have some fields in our theory. We have our parametrization, Gauss C and B, that have some conformal weight over here. We have the fields needed to bosonize the super-Gauss. And we have, of course, matter fields, X and psi, with, again, certain weights. Now, there are 2 conserved charges that are of interest to us. It's the Gauss charge, and the assignments are listed in this table, and the picture charge. Now, the Gauss current and the picture current that we are going to use are displayed over here. They are chosen in such a way that the picture changing operators that I'm going to present have Gauss charge 0. which is actually convenient for our purposes. Okay, so the next thing we need to combine these fields to construct physical states. Well, physical states are correspond to clauses in the we have been told in the semi-relative BRST cohomology, which means these are states which are annihilated by the total BRST charge, and moreover, we also have to impose the condition that the states are annihilated by B0 minus B0 tilde. Now, this cohomology is difficult to deal with, particularly because it doesn't factorize between left and right. So we have only statements here about the difference or the sum of these objects. And there are still some issues about this cohomology that I'm going to, to mention during the talk. Now, but it turns out that for the type of computations we want to do, which means if we keep the momentum generic, so if the momentum, which means that the momentum should not be equal to 0, it should be any non-vanishing value. And for the case that we are only interested in computing disk amplitudes, where we can prove the decoupling of BRST trivial states, there's something simpler we can do. Namely, it is possible to show that we can always pick a representative of this cohomology which has left and right conformal weight 0, ghost charge 1, 1, and which is annihilated by Q on the left and by Q tilde on the right. So each time I write one operator, just like Q, for example, it's going to be left mover, and if I put a tilde on it, it's going to be the right mover. So as long as we keep the momentum non-vanishing and compute disk amplitudes, then we are good. So then the only thing, so we can do something that factorizes between left and right. Again, so there are some, we can always find one, so up to BRST trivial terms, an object like this, defined like this, will be equivalent to an object in the semi-relative cohomology. Now, so what kind of states do we consider? Well, there is the NSNS sector, where we can have, well, the dilaton, the graviton, and the antisymmetric tensor. And this is the associated vertex operator. It's well known. So we have something here on the left, so a vertex operator depending on Z, and a vertex operator depending on the bar. And we have a polarization tensor here, which can be like traceless, symmetric, which can be a trace for the dilaton. It can be symmetric traceless or antisymmetric, depending on whether we have the dilaton, the graviton, or the B field. We will be using different supergauss pictures, and the vertex operators are, of course, well known for H's. Now, the situation is a bit different in the Raman-Raman sector. So again, we write the vertex operator as a product of something depending on Z over here, and something depending on the bar. And we have a coefficient here, which is basically given by the Raman-Raman field strength, contracted with some gamma matrix in some obvious way. So C over here is a charge conjugation matrix, and A and B are spinor indices. Now, so if both pictures are in the -1/2, or if P and P tilde are equal to -1/2, this vertex operator is of course known. So SA over here is a spin field. But if we are in the asymmetric picture where P, let's say, is equal to -1/2 and P tilde is equal to -3/2, this vertex operator is new. At least we couldn't find it in the literature. So there's an expression for this vertex operator in the literature by these people over here. However, this vertex operator had two features that we didn't like. It did depend on the Ramon-Ramon potential instead of the field strength. And moreover, it was a sum of infinitely many terms, and that's, of course, not very practical. So we actually were able to come up with an expression that is quite simple and depends on the field strength. So if it depends on the field strength instead of the potential, we are guaranteed gauge invariance from the very beginning, so we don't have to work to show it. So this is why it's practical for our purposes. So the next thing we need, so these are the closed string vertex operators that we are going to use. The next thing we need is to impose boundary conditions. So we compute disk amplitudes, there's a boundary. So we have to impose boundary conditions. Now, these boundary conditions are, of course, imposed here on the boundary of the disk, but it's a bit easier to actually map the disk to the upper half plane, so the boundary conditions take an easier form. So, given some primary field of field h is equal to h tilde, we want to impose conformal invariant boundary conditions. So what this means is the boundary conditions should be left invariant by those conformal transformations which leave the real axis invariant, the boundary of the upper half plane. Now, and this actually translates into a condition like this. Let's say O and O tilde are the holomorphic and anti-holomorphic part of a primary field. So R over here is a matrix with constant entries, which specifies the boundary conditions. So, for example, if we talk about dx, so this is what we would impose on the upper half plane, and D is a matrix, which will appear again later in this talk, with entries like plus minus 1. So depending on whether we have Neumann or Dirichlet boundary conditions. So depending on whether we are in a direction that is along the brane or transverse to the brane. So again, on the upper half plane, the boundary conditions are simple. We take this, we map this using a conformal transformation to the circle, and then it just gets a little bit more complicated, but it contains the same information. Now, so this is for classical fields. In a quantum theory, what we do is to use a boundary state to impose these boundary conditions. So basically, with the objects all become operators, which acting on a boundary state will give us a condition like this. Now, for practical purposes, so once we get to the point where we compute an amplitude, we actually never really need to know what B is. So people have constructed some of these, but all we actually ever need to know is this boundary condition over here. And once we have a correlator and we have some vertex operators, what we are going to do is to replace all the tilde oscillators like this by non-tilde oscillators. So we are going to write everything in terms of left movers, and this way we can get rid of the boundaries. And we basically end up computing a correlator on the sphere. So anti-holomorphic fields are then reflected back as holomorphic fields. Now, to obtain the, so starting with a complex plane, to obtain the disk, what we do is to identify 2 points, let's say z and z prime, where z prime is equal to 1 divided by z bar. And then the boundary is, of course, z bar square is equal to 1, the unit circle. Now, to obtain RP2, we do something similar, except we flip a sign. So we start again with a complex plane, and we identify 2 points z and z prime, where z prime is now equal to minus 1 divided by z bar instead of plus 1 divided by z bar. And again, so there are some, it's not boundary conditions now, but more like some identifications. So RP2 doesn't have a boundary, but we impose identifications like this. But basically, the technology goes through. So once we understand the boundary state, we understand also the cross-cap state. There are a few additional subtleties that we are working on, but we think we have reserved. Okay, so we have our vertex operators, we have our boundary states. So now we want to put everything together to compute an amplitude. To show how we do that, I'm going to present a cartoon, and then I'm going to translate this into a formula. So we have our, let's say this is a cartoon for a 3-point function. So we have first of all, we have the complex plane or the sphere. We have 3 closed string vertex, or we have 3 vertex operators located at z1, z2, and z3. We take care of the boundary by inserting a boundary state here at the south pole, and we use a propagator to take this boundary state to the point where we have first insertion, which at this point, which here is z3. Now, so this is the idea, which we then convert into a formula that looks like this. So we have, so this is our definition for our endpoint amplitude of closed string vertex operators on the disk. So we have, first of all, two standard vertex operators, V1 and V2, of the type that I've presented to you a few slides ago. And then we have to use the remaining vertex operators have to be of the integrated type. So if we compute an endpoint function, which basically means we take a standard vertex operator V that has got all the CGOs and everything in it, but we have to get rid of some of the CGOs by computing this commutator and anti-commutator. Now we need to do that in order to get a non-vanishing result. Otherwise, we just get equal to 0 because of Gauss charge mismatch. So then we have, and this is also the reason why we have to include this term here, B0 plus B0 tilde, otherwise we get 0. What else? So then we have our boundary state here. Again, that was inserted at the south pole. And this over here is a propagator that we get after mapping the cylinder to the complex plane. So, and again, it's propagated to, well, to the first insertion, basically. Now, so this is the definition of an endpoint amplitude. And so we want to make sure that this object makes sense before doing anything with it. Otherwise, we get a big formula and we may not understand it. So it's possible to show that the amplitudes so defined are independent of irrelevant choices. So what are these choices? So again, so this should probably be proof that we thought they should have been in the literature somewhere. We couldn't find them explicitly, so we read it the whole story. So the amplitude should be, first of all, independent of so the gauge choice, which BRST representative we use for each operator. And this amplitude should also be independent of the distribution of picture charges. Now, besides telling us, so these properties, besides telling us that these amplitudes make sense, are also useful technical tools. So once we have computed an amplitude, we get a big formula. We want to double check it. So we have, and one of the ways of double checking is to compute it in different pictures and comparing. So it's actually a non-trivial check and quite useful. So both of these statements require the decoupling of BRST trivial states from amplitudes. So the proof for an endpoint function is in our paper. Let me sketch how it works for a two-point function. So let's say we compute, using the procedure I just explained, we compute a two-point function of two vertex operators. One is just a physical state. The other one is BRST, exactly like this. With a little bit of work, we can turn this expression into something like this. So this it is actually a total derivative. If on the disk we introduce polar coordinates r and theta, then this is a total derivative over r. So we get to boundary terms at r is equal to infinity and 1. We are doing this in the outside of the disk, but it's the same. We can map it to the inside. And we get this integral here over theta. Now, this correlator is independent of Z1, so if we want, we can simply send Z1 to infinity. And then we look at the expression and we see how it depends on R. So it turns out that for R goes to infinity, the integrand depends on R in this way over here. So P1 and P2 are the two momenta of the two vertex operators. And A is like a number, 2, 3, 1. So some finite number that we know. Also at R is equal to 1, well, we check the amplitude and see what we get. Well, then the R dependence looks like this. So it depends on the momentum that is like transverse to the brane. And again, B is some number, some finite number that we know. Now, so the argument here is then to say that so this amplitude should be analytic functions in the momenta up to maybe some isolated poles. So it turns out that for a finite for an entire range of momenta, these boundary terms vanish. So over here we want this coefficient here. So for any given A, we can choose the momenta so that the exponent here is smaller than 0, and near r equal to 1, we want this object here, of course, to be positive. So for any given b, we can make the thing and exponent positive. So there's an entire range of momenta where these contributions vanish, and then we use analytic continuation to argue that well, this has to vanish everywhere. So this means these boundary terms have to vanish exactly, and BRST trivial states decouple. Now, it's also possible to show that the amplitudes are independent of the distribution of picture charge between the vertex operators. To show this, one introduces a picture, this object over here, x of z. And it turns out, so this operator, it commutes with a BRST charge, it has ghost charge 0 and a picture charge +1. And we can use actually the 0 mode to, so given any vertex operator corresponding to some physical state in some picture P, the 0 mode of this acting on this vertex operator creates another vertex operator for a physical state now in picture P +1. So, and it turns out that this 0 mode commutes with all the vertex operators up to BRST trivial stuff, that as we have seen the qubits from amplitudes. So this means that we can simply push x0 around in the correlator, and we see that the result is picture independent. Now, so we can change, this allows us to change pictures in the holomorphic pieces of the vertex operators. And well, we can also then, by realizing that x0 commutes with b0 plus b0 tilde, and that by acting on the boundary state we get x0 tilde, so the same operator but just with right moving fields. So then we can also change pictures between holomorphic and anti-holomorphic pieces. Now there is, so in principle, strictly speaking, we would also need to construct a picture lowering operator. Now, even at the level of cohomology, so if we want to show that cohomologies in different pictures are isomorphic, we need, so this is like a picture raising operator, so it sends p to p +1. Now, this operator is a bit more tricky. It has been discussed by these people. But it turns out that as long as the momentum, again, so this is where the condition of non-zero momentum enters. So as long as the momentum of the states is non-vanishing, so which means just as a vector, it shouldn't have all the components equal to 0, not just the physical state condition. So as long as that is different from 0, there is a picture lowering operator. And one can show that the cohomologies in different pictures are isomorphic. Now, if the momentum is equal to 0, identically to 0, then, as they have discussed, the semi-relative cohomology is actually picture dependent. So what this means, I don't know, and it seems like a puzzle that has not been resolved, but again, it's for very special states. All right, so I've showed you the tools that we use to build the amplitudes. I've shown you that whatever we compute with are reliable objects. So let's consider a concrete example then. So let's consider a two-point function here. Now, so it's a two-point function of a Raman-Ramon field in picture -1/2, and then in SNS state in picture -1, 0. We are, of course, not the first ones to compute this amplitude. It has been computed by these people and different subsets of these people. But still, before doing any serious work with this, we wanted to double check to make sure that this quantity makes sense. So we showed, for example, that it's picture independent. So we chose different vertex operators, and it's a small, non-trivial exercise, but it's actually good for you to check that yes. So in different pictures, we get the same result. Now, so what do we have on the right-hand side? So we have, first of all, the momenta P1 of the first vertex operator. We have P2, momentum of the second vertex operator. We have, again, this matrix D. which has entries plus minus 1, so plus 1 for directions along the brane, so if A and B are directions along the brane, and minus 1 for directions orthogonal to the brane. We have different combinations here of this momenta, so these are some scalar quantities. We have the polarization tensor epsilon of the vertex operator in the NSNS sector. And this object T here, well, it's a so F, again, is the Raman-Raman field strength of whatever degree we want to consider, and contracted in some obvious way with gamma matrices, and, well, we have to compute this trace. So we have a nice formula, so what are we going to do with this? Well, we are going to use this to construct brane interactions. So let me sketch how we do this. So the string amplitude looks sort of like this. The disk amplitude can be deformed into this object. So what we want to do is to take the field theory limit. So, and here's the reason why string theory amplitudes are nice. So this is one amplitude on the left-hand side. Now if we take the field theory limit, we get already 3 amplitudes on the right-hand side, which means basically we are taking the size of the tube to 0. So the solid lines are Raman-Raman fields of different degrees that are specified over here. The dashed lines are B fields. So we have as external states a Raman-Raman field of degree p minus 1 and the B fields and all of these. And the wavy lines here are like gauge fields on the brane. So the interactions, the new interactions that we want to construct are encoded in this vertex over here. So there's nothing new in any of the remaining vertices. So here's what we have to do. We take the string theory amplitude, we expand in powers of the momenta, we subtract the field theory result for this diagram and this diagram, which, just to show you that we did our homework, here's the result for the field theory diagrams. So we subtract these 2 contributions, the one from A and from B, and we are left with a contribution from C. Well, this is what then the contribution for C again encodes the effective action, so a term in the effective action that couples CP minus 1 form under B field. Now, so to leading order, so I'm just not quoting here any constants, just to keep things simple. So the resulting action that couples C and B on the D-brane has several contributions. So we start at 0 order in derivatives, then the first correction appears as 4th order, and there's of course an infinite series. Now at 0 order in derivatives, we get this term, which is of course well known. It's like, so if we have a D-brane, that's like an interaction like this, which we of course know. So here epsilon is like the volume form on the brane, but then we get these corrections here to 4th order in derivatives. So this effective action then encodes the corrections to the vertex in over here. So this is a correction to the D-brane, action. So this was so in this example the formulas are short, so I can show them to you in a slide and more or less explain what we did. Now this is not just a toy example, some interactions that we want to compute, but it's actually an ingredient that we need in order to extract interactions from a 3-point function, as I'm going to explain in a moment. So this correction here to this vertex that I computed here, or that I showed you that we computed, is going to play a role in a moment when we extract interactions coupling 3 fields. So let's next discuss the 3-point function. Things are of course more complicated. So here's the 3-point function, and that's all I'm going to show you about it. So it's a 3-point function on the disk of a Raman-Raman field, now of degree p minus 3, and 2 B fields. And well, so it's some formula. I mean that's that's long. So we want to use this to extract interactions on the d-brane volume, coupling the three fields, and again, which are fourth order in the derivatives. So we take this big expression that I'm not showing you, so let's simply assume that you know how it looks like. We take the small momentum limit, and then we want to compare with field theory. Now, in this situation, things are already a bit more complicated, because the possible field theory diagrams that appear are this one, so we have 6 diagrams. Now, the interaction we want to extract from here is this last one. So this vertex couples two B fields and a Raman field of degree p-3 on the brane. So that's what we want. But we have all these other diagrams that I like to call background noise. So we have to subtract 5 field theory diagrams. Now, some of these field theory diagrams are easy. For example, to A and to C. So these diagrams are easy because they are not corrected to the order alpha prime square that we are interested in. So, for example, the space-time vertices, if they get a correction at all, it would be like to order alpha prime cubed. So, because this is how the type 2 effective action looks like. So, this one and this one, to A and to C, we can simply write down some formula, however it looks like. Now, these ones, to B, D, and E, are a bit more tricky, because as I have just shown you, this for example, explicitly for this vertex, this is corrected to order alpha prime square. So we first have to compute corrections to this vertex, and to this one, and then we use it as an ingredient to compute to B, to D, and to E. So let's assume we did that, and then we can extract from there this last diagram. Well, again, so the action is going, so this is what we find, so this is the effective action. Now, there's of course an L is again given like by L0. The starting term is fourth order in the derivative expansion. So L0 in this case is of course again well known. So in this case it's like Cp-3 wedge B. So I'm not quoting that because that term is known. But this is the new interaction on the d-brane volume. Now I've given talks before about this topic on different occasions, but it's the first time that I can actually present this action in a closed form and claim that this is our final result. Now, there are different ways of writing this, and I've chosen this because of different reasons. First of all, this includes couplings that have 3 fields, like this one, so it's like B, and C over here. But I've also included stuff that includes only 2 fields, so the result for that we got from the 2-point function is also included here. Now, so, by construction, this agrees with the result from string scattering amplitudes, of course. Now, the reason why I chose to write it like this is that invariance under an SNS and Raman gauge transformations is obvious, because the result depends, first of all, in SNS gauge transformations, the result depends only on H, on dB, over here. Or it depends on B tilde, which is the gauge invariant combination of B and the U1 gauge field on the brane. And it can be written in terms of the Raman field strength like this, so that also invariance under Raman gauge transformations becomes obvious, which may not have been obvious maybe from a formula like this. So if I present this, you could have asked, so why is this invariant under Raman gauge transformations? Well, you have to do a computation. Here you don't compute, you just look at it. Now, there were some terms known in the literature before that they are not easy to identify in this way of writing the action, but yes, we agree with all the previous results in the literature. Now, so this, the next property that I want to discuss a little bit more in detail is that this action is actually required to restore consistency of string theory, Without this, T-duality would be violated. So let me take a small detour and explain how all of this relates to T-duality. So there is a basic condition that any D-brane action has to satisfy. It has to be compatible with T-duality. Now, so this cartoon explains what this means. So imagine we take a D-brane in type 2A, we compactify on a circle, which is transverse to the brane. The D-brane stays a D-brane, a D-brane. And then we do another exercise. We take a dp plus 1 brane. We do a double dimensional reduction on the dual circle. So the dp plus 1 brane becomes a dp brane, while T-duality tells us this should be the same. So that is basically the tool that we are going to use to actually find a different way of computing these amplitudes and then compare with a result from string scattering. So most terms in the D-brane Lagrangian are of course compatible with T-duality. This has been known for ages. Not sure who to blame for this, probably maybe people like Berkshaw, van Barboon. It's also reviewed in the paper on dielectric branes by Myers. So it's a small exercise to show that the D-brane DBI action, the Bern-Infeld action, is compatible with T-duality, or also the Vesumino action. Now, but these are of course not all terms in the D-brane effective action. There's stuff beyond leading order and derivatives. So here's an example of such an interaction on a D7 brane volt volume. It involves the Raman-Raman 4 form and different types of curvatures on the tangent bundle and the normal bundle. This is of course only a special type of for derivative coupling that involves curvature. Well, there can actually also be more than 4 or 8 derivative couplings. So this is a special case of some couplings that are formulated in terms of the area of genus. But it's actually enough for our purposes. As I will show you, it's complicated enough already. So there's this on a D7 brane, and again on DP branes there's similar stuff. And there's also similar couplings on Orion default planes. So people have found this some time ago using different arguments. And it has also then been checked with explicit amplitude computations. Now, but this is all they told us that there would be, so something involving the metric. But this cannot be the whole story, of course. Since it involves only the metric, just imagine we take an interaction, a dp brane volt volume, which is like a circular bundle over some base, and there's an isometry in one direction, let's call it y. So we apply a T-duality on this direction y, and let's assume we have a metric component in this direction, some kind of off-diagonal entry. We are going to generate something involving the B field, of course. So the question is then, what is the, that we want to answer, what is the T-duality invariant, which includes this object over here. So we have part of the answer, not all of it. So in principle, this doesn't require much technology, but lots of patience. So you take this object as is, you apply your Busher rules like that, you generate a new coupling, and in principle you could be able to, if you have enough patience, to classify all possible terms that can appear and try to guess what is the T-duality invariant. Well, that exercise is too hard and we still haven't solved. So in order to simplify our life, and since you, as you may have guessed, whatever interaction I'm going to predict here using T-duality, I want to compare with the result from string scattering amplitudes. So to simplify our lives, what we are going to do is a weak field expansion. Because this is also all we ever get from string scattering. So what we are going to do is to expand the metric like this. G is equal to something flat plus h. And we are going to look this as fluctuations in h. So we are going to expand in the number of fields, and the Busher rules become much nicer already. the Ramon-Ramon forms of different degree transform in a, of course, well-known way. So then what we want to do is to also expand our favorite interaction here. So let's write it for a D-brane in this form, not only on a 7-brane. So X4 is this 4 form. Again, with a bit of patience, you expand in the number of fields. You choose your static gauge, expand in the number of fields, etc., etc. So here's the expression you can come up with. So you have like 4 derivatives with different index combinations acting on H. So we have, let's not consider this factor e to the b. So let's simply talk about C. So we have one Ramon-Ramon field and 2 gravitons over here. Now again, A and B are like indices along the brane, I and J are indices orthogonal to it. Now, so again, now the exercise of trying to guess the T-duality invariant coupling seems to be within reach, but now I want to convince you that it's still a difficult problem. So the reason why it's a difficult problem, and I want to take a moment to stop and explain this picture. So the reason why it's still a difficult problem is the following. So we have seen on a D7 brane a coupling between C4 and 2H, let's say 2 metric. Now on general grounds, we can argue that the D-brane effective action is going to have the following, is going to include the following fields. Now, so what this table shows us is what brane coupling, and this only displays the fields that are involved. For example, this coupling over here involving CP-1 and B, I would represent as something like this. Now, the coupling, just to orient ourselves, the coupling that did involve like this. So C4 and 2 metric, is this little piece over there. So this holds for any number of derivatives. Now, on general grounds, we can argue that the different fields that can appear in the different interactions look like this. So if we have something proportional to CP-3, it's going to have either 2 metric pieces, or it's going to have 2 B fields. Now, then there can also be couplings that involve CP-1. These have to be of a different type. They have to mix B and H. If it's CP+1, it's again like B and B and H, etc. Now, so again, we have expanded in the number of fields, so we would continue here. The dots contain like more fields, but we haven't done anything with those yet. Now, what the arrows indicate is how T-duality acts. Now, so a solid arrow would mean like T-duality at the linearized level. So it tells us, so the arrows tell us how different, under T-duality, how different interactions mix with each other. This is T-duality along the brane. This is a T-duality transverse to the brane. So for example, V coupling over here that involves 2 metric, that is the one that we were given from the literature. So that under T-duality, it has to map to itself, so it should mix with some interaction involving 2 B fields. But it also mixes with other interactions like that involve CP-1 and so on. So it's a difficult problem because we have to combine. So in order to find the T-duality invariant that includes the gravitational piece here, this CP-3HH, we actually have to combine different terms. Now, so the reason, maybe I should, before going on, explain one additional thing. So the reason why we have this pattern, so that there's only like 2 B fields here and 2 H, and 1 B field and 1 H, and like this. So there will never be something that involves CP-1 and 2 Bs. Has to do with a certain Z2 symmetry in our amplitudes. So this is actually the same symmetry you mod out by if you want to create an oriented plane. But we don't want to mod out by it. So we just want to use it as a symmetry. And a little bit of thought shows that, so this transformation, what it does is to transform the momenta of the different states, the polarization tensor of the SNS state, and the Raman-Raman field in this way. Now there's lots of stuff on the right-hand side we don't care about, so we can actually forget the D's because they are contracted with each other. And all we care about is this epsilon being transposed, and this factor here, -1 to the k plus 1. So you know that it's a symmetry, and so if you get a -1 after doing this transformation, you get 0. So this correlates, so the degree of the Raman-Raman form over here to the number of B's and H's. So, as I said, without much technology, so just patience, we want to guess what is the T-duality invariant that includes H. Well, here it is. We actually have been able to come up with a T-duality invariant that includes only this coupling, this one, and this one. So this 3. It doesn't go all the way up, at least not in to the linearized level. So at the linearized level, this over here is a T-duality invariant. So I have to tell you what this objects x4, x3, and x2 are. So x4 includes the gravitational piece and additional stuff involving the B field. Now this is not pretty, so it has many indices and it looks ugly. But well, trace of ROHR is not pretty either. I mean, it has many indices and looks bad. So this doesn't mean that there isn't maybe some nice formulation of this coupling that just becomes ugly once we expand in the number of fields as we have done. So, but this is what we have, such is life. Just to show you that we did our homework, this is x3 and x2. So, and it stops there. So this is all we need to construct this T-duality invariant at the linearized level. And guess what? Yes. In the first part of the talk, I showed you how we extracted an interaction involving CP-3 and 2B fields. And guess what? The results, of course, agree. Otherwise, I wouldn't be telling this story at least not in the same talk. And here are new interactions involving B and H. And yes, we also did the string scattering amplitudes. We computed them. And all the results from T-duality agree with the result from superstring scattering amplitudes. So this was the computation we did, but it's clear that we only scratched the surface here. So let me finish or conclude with a list of things to do. So let me go back to this picture that shows a map of all the possible couplings again. So this one was known in the literature. Now we have nailed down completely this last coupling over here. We know some pieces of this coupling and some pieces of this coupling using T-duality and using string amplitudes. The results agree. But of course there are many more couplings here for us to compute. Now, then we will only know fragments of these couplings, and fragments may not be nice. In the same way as the fragments of this coupling here are ugly. So if we expand, maybe if we can find some let me call this T-duality completion, which is invariant under nonlinear Busher roots, we will come up with a nice object. But so this is still a different. This is still a difficult exercise, and all we know are the fragments. So this, of course, then addresses here the next point. So we want. Ideally, we would find the T-duality completion, which includes also this coupling. But again, in general, it's difficult. Something that we are doing concretely now is to compute RP2 amplitudes, and I've mentioned this briefly. I mean, all it does really is to replace the boundary state by the cross-cup. Now, but for orientified planes, things are actually much easier. We sort of have started with the more difficult problem because there are less fields, so there are no gauge fields on the brane. And it may be much easier maybe to come up with a closed expression. There also seems to be a relation between cross-cup amplitudes and disk amplitudes. that we can work out using an old trick by Kawai, Levin, and Antai, and that we are exploring right now. Now, ideally, we would also be able to set up, so we have computed amplitude on the disk and on the cross-cup. But in general, any worldsheet would have like an arbitrary number of handles, cross-cup, and boundaries. And it would be interesting, I mean, we don't know how to do this, to set up the technology to compute some of these. There are, of course, many more problems, open problems, but I want to leave you with that. That's all I wanted to say.
Thank you very much. Other questions?
I have the impression that there's some that in the anomalous couplings on O-planes that there are different results in the literature. One set of results that follow from kind of duality chasing, and the other from more formal mathematical K-theory arguments. Do you have any? Do you shed any light on what's going on there?
Well, we can shed light on to those that are called like O plus and O minus planes, not on those that are called like tilde, O plus tilde, and O minus tilde. There the result is that follows from string scattering amplitudes is that they differ by a sign.
Can you remind me which ones are the ones where there's a disagreement?
So there was a disagreement between, so O tilde ones are more complicated because they are not in perturbative string theory. But even for O plus and O minus, there's disagreement in the literature, so there are different results. And the result from our computation, that's something we looked at, is that they differ by a sign. So this was a claim of some people in the literature, but not in others.
For a three-brane, you've got S-duality as well. So can you use S-duality to restrict the couplings there between B and C, and then T-dualize?
Suppose one can do that. I mean, I think people have done this. People like Garuzzi, for example, there has been some exercise. It's not something that we have followed, so we first wanted to find the complete result. But yes, in general, I suppose you can.
If there are no further questions, let's thank the speaker again.